Okay. I have a sad, short announcement that, as I expected, we have already one positive COVID test. So the rules changed a little bit. It's highly recommended to wear the mask here. You can have some masks there, and there's the disinfection solution. And yes, so John, who hates the mask, it's highly recommended. You don't need to wear the mask, but it's highly recommended. We have few rapid tests, but we can order some more. If you want to have some rapid tests, then please go, when you go to the lunch, please go to the registration desk, and they will collect the requests. One rapid test costs 2,000 Hungarian euros, not Hungarian forints. 2,000 Hungarian forints, not euros. 2,000 Hungarian forints, which is 5 euros. 5 euros. If you feel bad right now, I can give you some rapid tests. And then it's, if you test it positive, then stay in your room. You will get the food in your room. So the participant who had the positive test is staying in the room, and he is online. And also the hotel will disinfect this room with ozone when we are on lunch and when we are on excursion. And also we started the YouTube channel, the real-time YouTube channel at the registration area. So if you want to go, you can watch the conference from the registration area, where you can keep more distance. Okay, and if you had any questions, then come to me, and I hope that we can solve this issue. Thank you. Yeah, the speaker should, I think.
Hi, this is me again. So I will share this second session, and this is my great pleasure to present Robert Kolos from the Institute of Physical Chemistry in Poland, and he will talk about photochemistry and spectroscopy of small matrix-isolated organophosphorus molecules. Please, Robert.
Thank you very much, Rotara, and I would like also to thank organizers for the invitation and for all the work here. We are witnessing that every minute, and there is more to come. Okay, so we've been actually interested in the phosphorus-containing unsaturated molecules for quite a long time, and obviously we are inspired by the importance of interstellar nitriles. Now, some examples of that, we, for instance, were working on the isomerization of cyanoacetylenes and dicyanoacetylenes. This is just an example, the isomerization of the shortest cyanopolyacetylene, namely cyanodiacetylene. We were able to actually identified these three, experimentally, these three isomers, the new molecules. This has been done in collaboration with the with a group in Marseille, and actually practically all the research along these lines that we have done in Warsaw, it was in collaboration with the French groups, either from Orsay or from Marseille, in some instances from both these groups. So this is, for instance, in other topic, the coupling of unsaturated polyinic chains in matrices, in, well, apparently rigid matrices, but it works nevertheless. Another example is the work on the anions, cyanacetylenic anions, the spectroscopy in infrared, and very importantly the luminescence spectroscopy, the electronic luminescence spectroscopy. Now the last of these papers, as you may perhaps see, is quite fresh. I will, however, not talk about this today, but rather in our recent interest in looking, well, down the periodic table a little bit. Below nitrogen you have phosphorus, and phosphorus is also an important ingredient of interstellar molecules. And well, it is also very important, of course, from the planetological point of view. The molecules I will concentrate on today, these are just 4 species, so this is the title for today. And the molecules, these molecules are just 4 species that I have used as the photochemical precursors, namely the analogs of nitriles, simple nitriles, and amines, that is the phosphines and the so-called phosphoacynes. So let me start with the first of these, namely an analog of acetonitrile. Now, when you look at the isomers of acetonitrile, the predicted energies of these, then you will find, well, that some of these actually have not been observed. These are grayed out here, but the most stable modification of acetonitrile, isomeric modification, is that molecule here. As you may have guessed, this is simply an isonitrile. But when we compare it with the family of analogous phosphorus-containing species, there is not much in common. Well, one important thing in common you can see, and this is that the lowest energy species have the same structure. But apart from that, everything is different. And for instance, and very importantly, the analog of isonitrile has never been indeed observed. This is the least stable of all these species. And the most stable one, according to the predictions, is that phosphoalene structure. Now, when we put phosphopropyne, that molecule here, when we put it in a matrix and photolyzed, then we could easily see actually this very molecule. So from that point on, it can be considered as a non-species, and you can see in a picture one of my postdocs, one of the postdocs in my group, who is happily holding the molecule. It's like putting the hands of something new, right? But this is only like a mere, a stable intermediate on the road to further products, and the molecule isomerizes then into this into that derivative of acetylene, alanine phosphine. And the interesting thing is that when we did these experiments with isotopically labeled precursors, because we have used the deuterated precursors and C13 labeled precursors. So with the C13 labeled molecule labeled at the methyl group, we could see that this product here, this acynyl phosphine, has been produced in as two isotopologues in a 50-50 ratio. So that that labeled carbon was either far away from the phosphorus as you would expect, but it could be also actually close to the phosphorus. So the only logical conjecture, I believe, is that we must have a cyclic intermediate between. Now this is a phosphorine structure. Normally this is a stable compound that has been isolated. So we haven't found it in a matrix. Maybe it isomerizes too fast, and maybe our cyclic intermediate it is not just the phosphorine, but in other structure like a saddle point on the cyclic structure on like a saddle point on a potential energy surface. We have not finished the theoretical analysis of that case, which may be of some importance. But this is not the final product of the photolysis, and the crucial product, the final product, which is produced with a yield well above 60%, is that molecule here. So this is HCCP. This is not obviously the isomerization product by a photodehydrogenation product, and such molecules are called phosphinidines. Strange creatures, because formally you have a single phosphorus carbon bond here, not as we have learned at school that phosphorus should be either trivalent or pentavalent. So here it is not. Now, okay, so this is an infrared spectrum that shows the identification with the predicted spectrum with having the absorptions pointing downwards. Yeah. Okay, so we have it there. It has also been verified in these isotopic experiments, and there is also an associated electronic absorption spectrum. And we have also, and by we I understand here the postdoc in my group, Aaron Lauser. So he has measured the EPR spectrum in the Professor Wolfram Zander's group. I cannot give you the zero field splitting parameter yet, because this is still under analysis, the spectrum, but it is obvious that the E parameter is zero, so this is a linear molecule, and the D parameter is like with other phosphinidines, I mean close to that. Okay. Other phosphinidines, it may sound as if there were many other phosphinidines, and this is actually not the case. So these are electron deficient species, just like nitrines, the analogs of nitrines or carbines to some extent, and there are not many of them known. These are triplet species. Of course, this is why we have measured the ESR spectrum to start with. And apart from the archetypical molecule, diatomic molecule, the phosphinidine, or HP, there is, I believe that these molecules that you can see now, right now on the screen, are all phosphinidines that have been reported, plus, of course, the HCCP. So these are not many, and actually these are the triplets in the ground state, as I have said, with the exception of this beautiful creature here with the PP bond, and that one actually is stable at room temperature, as far as I know. So here you can see another of my postdocs, Aaron Lauser, who is happily holding the molecule, and this is like a, well, final proof that this is a phosphinidine, because if you look closely, you can see that there is indeed a single bond here. Okay. Now, another molecule, shorter one, simpler one, with just one carbon, phosphorethane, or methylphosphine. So the photolysis of that molecule yields phosphorethene or phosphorethylene, and we could indeed see it and characterize the infrared absorption bands. But again, this is but an intermediate, a stable intermediate, en route to further photolysis, and the final product of that photolysis is HCP, an analog of hydrogen cyanide, together with some admixture of the CP radicals. Now that HCP molecule requires a comment, because this is a very special species. You can see this lady on the screen, Vera Popova. This was one of the best-known women in chemical science at her times, that is at the second half of the 19th century. And she actually received a PhD grade in Switzerland, and allegedly her supervisor discouraged her from following her dream, and so she completed her PhD with something else than that dream. And the dream was to synthesize an analog of hydrogen cyanide. She returned to Russia after receiving this her grade and continued in chemical research, and she tragically died in 1896 at the age of only 29 in an explosion that occurred when she tried to synthesize an HCP. So I don't know if there is a take-home message here for the PhD students or not. Perhaps not, rather not, but that was just the case. And the molecule has been synthesized in 1961. So in modern times, for the first time, and it was in discharges through phosphine pH3 between carbon electrodes. And since that time, the molecule has been synthesized by several different methods, and it can be considered as a known species, both theoretically and experimentally. It's, I mean, spectroscopically. Practically everything is known about HCP, a lot at least, but I couldn't find any paper on the photochemistry of HCP, in fact. And perhaps for a reason, well, one of the reasons may be that it is hard to obtain a pure substance. So for the spectroscopy, it doesn't matter very much, but for the photochemistry, you would like, however, to start with a pure substance to know what's happening. But the other reason may be even simpler, maybe because this is not so very interesting to photolyze HCP, because what can you expect? It should just produce a free radical CP and hydrogen. But this is exactly what we wanted, actually. We wanted a clean source of CP radicals. And we are happy to collaborate with Jean-Claude Guillemin from Rennes, famous organic chemist whom quite a lot of you know, I think. And he is known for his ability to synthesize otherwise hard to synthesize compounds of astrochemical significance. So he knows how to produce this dichloromethyl phosphine. He knows how to get rid of HCl from that molecule and how to obtain then the pure HCP product. So once we had it, we have photolyzed this in a matrix, and And yes, we did observe the CP radicals. Now, the spectroscopy of CP is, the known electronic spectroscopy of CP is rather boring and very similar to the spectroscopy of the CN radical that has been extensively studied, of course, since almost the beginning of spectroscopy. So you have an analog of the violet bands of CN, you have an analog of the red bands of CN, and even an analog of the so-called Leblanc bands of CN between the B and A states. So in our matrices, after the photolysis of HCP, we could indeed see this BX absorption, exactly where we could expect it based on gas phase spectra. And well, we could also see the fluorescence. Actually, the all-known spectroscopy before these experiments of ours, it was based on the gas phase on the gas phase fluorescence spectroscopy, and so on the fluorescence, and it is something like 100 years old. This knowledge of these electronic transitions. It was Gerhard Herzberg who started that research well before the Second World War. And as I said, basically this is the same picture up to now. So we could see also the fluorescence in our matrices, the BX fluorescence, the BA fluorescence. We were not equipped to see the AX transitions, neither in fluorescence or absorption. Okay, but now when you have a molecule which is something like, for which the spectroscopy is something like 100 years old, and this is a diatomic molecule of popular elements, then you cannot expect to find something dramatically new in that picture. And yet this is what happened, you see, because we could see, apart from this fluorescence that I have mentioned, we could also see the phosphorescence, actually, in other emission. In other emissions that did not fit to the picture. And actually the excitation spectra of every band that you can see here on this screen, these excitation spectra match exactly. This is this red curve at the top. They match exactly the absorption spectrum, the BX absorption spectrum of the CP radicals. So this is a molecule which is, so this is an emission that is excited by exciting the BX bands of CP. There is no doubt about this. And this is actually a long emission. As you can see here, the lifetime of that is 100 milliseconds. So this is why I said it is a phosphorescence. Now it is actually not common to see a phosphorescence from the free radicals, as you may know. In decently behaving closed shell molecules, you expect the triplet state to be the lowest excited state, and there is a reason for that. The Hund's rule, and so that you may expect that that this triplet state acts as a trap for the excitation energy, and quite often one can see the radiative relaxation from that state, that is the phosphorescence. But with doublet, with free radical molecules of a doublet ground state, it is very much not so, because here you see, well, this is a pretty simplified picture, but at least within that simplified picture, it is what one expects is that the first excited the first excited doublet, the first excited state, in fact, SOMO here stands for the singly occupied molecular orbital. So that state is slower than the quartet, obviously. So you cannot expect a quartet to be the lowest excited state, and then it is pretty difficult to populate that quartet state, because you cannot populate it uphill, of course, and this is not expected to populate it from any of the excited doublet states, because the doublet internal conversion, that is the internal conversion in general between the excited states is very fast. So the intersystem crossing cannot compete with this fast internal conversion between the excited doublets. So how come? Why do we observe this emission? So the answer comes, we believe, from that paper, from two papers, recent papers of Chinese theoreticians who have calculated the potential energy curves for the CP radical. And as you can see here, there is an energetic coincidence between the second doublet, excited doublet state, and the second quartet state. They are almost isoenergetic, these two. So this is, we believe, what happens is that this closeness of these two states promotes the intersystem crossing. So even though the internal conversion is probably quite fast here, this non-radiative transition can occur with a reasonable yield. And then once we are in the triplet, of course, the triplet ladder of states, then we have this fast internal conversion to the lowest state of that multiplicity, and from there we can have phosphorescence. And actually, this is the spectrum explained. So we actually see a strong emission from the quartet A state to the doublet A state. These are these bands here, and we see a somewhat weaker progression of bands from the quartet 8 to the ground state, and we can see actually this splitting in the A state, doublet A state, due to the spin orbit coupling, as you can see here, and this splitting, the measured value matches the value known from the gas phase spectroscopy. Well, so this is about it. I watched this glimpse at our recent research interests. This is the work in progress. We are interested in extending this unsaturated unsaturated polyenic chains, and this is actually why we wanted a clean source of the CP radicals in the first place. So there is some progress here. It is too early to talk about this today. And the other line of research, it is looking even further down the periodic table. There is an arsenic atom there and an antimony atom, and the spectroscopy of the analogs of these simple nitriles or phosphines that with arsenic or antimony atoms is largely unknown. It is not very astrochemical. It is, if we go below phosphorus, arsenic a little bit planetological perhaps, but this is interesting anyway. And I would like to end with showing the people who are engaged in this research. So the current composition of my group in Warsaw, it is this Arun Lauser, the postdoc from India. You have seen him on the picture. The other guy in the picture, that was Thomas Custer, a postdoc from United States. Ilavenil Ganesan is a PhD student from India. Marcin Gronowski is mostly doing theoretical calculations in our group. I have mentioned the very important collaboration that we have with Jean-Claude Guillemin already, and I have also mentioned the collaboration with the group of Professor Zander in Bochum. And we have just started a French-Polish project that will deal, among other topics, with these phosphorus-containing molecules, so there is more to come. Thank you very much for your attention.
Thank you, Robert, for this didactic talk. Are there any questions?
Zasimov Pavel from Lomonosov Moscow State University. Thank you for the nice talk. As far as I understood, most of the species resulting from the photolysis of the methylphosphine and phosphorus-containing analog of the acetonitrile are closed-cell species. Have you detected any signs of the radicals resulting from the photolysis of the...
Sorry, once more, have I detected any signs of what?
Any signs of radicals, open shell species?
Well, the one radical species, of course, is the CP radical, but with some signs, perhaps, of the CPC, maybe, but this is in other research. But not really. Apart from CP, not much.
Because well, I expect that the photolysis of CH3 pH2 may probably result in formation of CH2 pH2 or CH3 pH. So
this is what we were looking for. And yes, well, some traces of a methyl radical and pH2 radical, perhaps, but this is not what dominates the photochemistry.
Okay, thank you.
So, in the case of your ethinyl radical, ethinyl phosphinidane, not radical, pardon. Mm-hmm. Have you done some NRT analysis to have contribution of the carbene there? You know what I mean? So you can make a resonance structure that
Absolutely. Yes, thank you for that question. Yes, so it is nice to say that this is a single phosphorus carbon bond, but in reality it is of course not so. And the calculations indicate that actually the leading Lewis structure is an allynic one with a double, that is with a double bond between carbon and phosphorus. However, the importance of that single carbon, a single bonded CP structure is also quite significant. So it's interesting actually to compare it to HCCN molecule, in which also the leading structure is this allynic one, and actually the other structure in HCCN is the one with a triple bond between nitrogen and carbon, so in each of these structures, of course, the position of these two electrons that formed a triplet is different. So these are not necessarily on the phosphorus. They can be on the terminal carbon, and then it is the allynic structure, Or in case of a nitrogen-containing molecule, they can be one electron on phosphorus and the other electron on the terminal carbon, and then you have a triple bond between nictogen and carbon.
And just continue. And if you compare that singlet-triplet gap for this ethinyl phosphanidane, it's actually smaller compared to other phosphanidanes, or it's bigger? What's the singlet-triplet gap? You know.
I cannot answer that question. Sorry, I don't remember how it is. It is actually similar that in HP, diatomic HP, if I remember correctly. But I don't remember how it compares to those aromatic to the singlet-triplet gap in these aromatic systems. So, sorry.
We have time for a short question, yeah?
Yes, I was interested in the CP radical, and in some ways it's similar to the N2 plus molecule and the CN molecule, I guess. And for those, I think there is some perturbation to the levels, the B state levels by quartet levels, which is apparent, I think, in rotationally resolved spectra. And I'm just wondering whether you're seeing the same sort of thing.
So yes, so the CN radical has been extensively studied, and there is some knowledge on the quartet states of CN, and it comes, as you have said, exclusively from the perturbations in the doublet transitions. The phosphorescence has never been observed, of course, for the CN. And when you look at the positions of the quartet and doublet potential energy curves, there is no grounds for that, indeed, yeah.
So you don't see, if you had CN in a matrix, you would not see any phosphorescence from the quartet level?
In a CN, you see?
Yeah.
No, absolutely not.
Okay.
Neither it is the case according to the calculation, for example, for an CAS radical.
Okay, so I think we can move on to the second speaker. Thank you again, Robert. So the second speaker is Joshua Baraban, who comes from Ben Gurion University of the Negev from Israel. And today he will speak about, so the title has slightly changed, about tunneling and ring opening in the cyclopropyl radical and cation. Please, Joshua.
Thank you. Thank you very much to the organizers for the invitation, for putting together this very nice conference. So in my research group, we are interested in developing new spectroscopic approaches for characterizing the physical and chemical properties of what I would call unusual molecules in, let's say, energetic environments. So this extends from, let's see if I can get this thing to work here, high temperature chemistry, transparent microscale flow reactors like flash pyrolysis that many of you are familiar with. We also work with cold plasmas, non-equilibrium cold plasmas. And I like to show this example here at the bottom left because it helps to illustrate to non-spectroscopists the kind of thing that we do, because you can see here, based on the colors, which molecules have been flowed into these plasmas. And just as one example of the type of work that we do, you see here at the top right this decomposition of biomass molecules, biomass lignin monomers, into smaller rings and radicals. And so this idea of a ring contraction, ring expansion, ring opening, and ring closing, this is the topic that I'd like to discuss with you today. We've heard a fair amount about it in several of the talks. And we, just for the purpose of having something that is cold here, we do some infrared spectroscopy in matrices. That's the data that you see here at the bottom right. But again, what I want to talk to you about is rings. And what we like to do is, when we get interested in a subject like this, is to go to the most fundamental, the smallest system that can exhibit this phenomenon. And we often find that examining this in great detail gives us a lot of insight into the concept, into this particular subject. And you'll see that this is no exception. So the topic of ring strain starts with Bayer in the late 1800s. And here, this is a figure from one of his papers. he attempted to rationalize the reactivity of various cyclic, as he considered them, compounds in terms of their geometry and the angles and connecting this to strain. And of course, Bayer knew nothing about the three-dimensional structure of molecules or about hybridization. But one molecule that he got correct is the cyclopropane, or in general, the cyclopropyl groups, because there's no other way to arrange 3 carbon atoms in space except in a plane. So Bayer got lucky on this one. And it's this sort of unique geometric property of cyclopropyl rings that continues to make them of great interest to organic chemists today because they're very important in chemical synthesis. This planarity of the ring enables certain regio and stereoselective synthetic techniques. And so, of course, the strain of these rings is very, very important for this. As we'll see, these cyclopropyl rings also have very unusual hybridization because of their strained structure. So they're very interesting for a number of chemical reasons. And we wanted to understand how these rings behave and how they open and close. And of course, we're not the first people to be interested in this. The original paper by Woodward and Hoffman about their rules for orbital symmetry in electrocyclic reactions discussed this very case. Not only cyclopropyl, but in other words, all of the possibilities. So cyclopropyl cation, radical, and anion. And so what do I mean here by the electrocyclic reaction? What's the ring opening and closing mechanism here? So you can see that there's this carbon-carbon-carbon bond here. We have to obviously open that up in order to open or close the ring. That has to change. But it's important to keep in mind that we also need to twist these CH2 rotors on either side, because when the ring opens, it has to come to some sort of allylic structure, right? Otherwise, this is very unstable. And so these are the 3 main coordinates that are involved in this transformation. And you can see here a figure from Woodward and Hoffman's paper where they illustrate this sort of ring opening and also this twisting of the terminal groups. And here's where things start to get a little bit more interesting. There's 2 different ways to accomplish this transformation, of course, and this is illustrated here on the bottom with this double-headed arrow here. You have 2 different ways, the con and dis rotatory paths, which preserve 2 different symmetries when you open the ring in one way or the other. And this, of course, leads to the orbital symmetry considerations of Woodward and Hoffman. And in this particular case, Christopher Longway Higgins published a paper shortly after Woodward and Hoffman's papers, and he pointed out that they had actually made a mistake, that they predicted that the cyclopropyl radical would open in the same way as the anion. And in fact, when you consider all of the orbitals, the full electronic symmetry of the wave function, you get a different result, which is a very interesting one in the context of Woodward and Hoffman, because as you can see here, ordinarily what Woodward and Hoffman rules give you, this pointer is very... so you can see here that in general, what do you see? That for either the disrotatory or the conrotatory, you have a barrierless path, right? In other words, there's a straight line here. And then in the other case, you have a crossing as you correlate the orbitals from the symmetries of the orbitals from one structure to the other. And this is what happens here in the cation. This is what happens here in the anion. You have one where one pathway is flat, and the other one you have the crossing. In the cyclopropyl radical, both paths are predicted to have a barrier. According to Longway Higgins, he actually invented the idea of correlation diagrams for this paper, note of historical interest. And Woodward and Hoffman quickly published another paper where they agreed with Longway Higgins that he was correct. But you can see that if we go several decades forward in time again here, this is a paper from Jackson in the 1990s. And so 2 things that I want to point out to you here. So one, they do not have this barrier in both cases. They predict a disrotatory path for the radical, which should be Woodward-Hoffman allowed. And you can also see here what I mentioned about the unusual hybridization and bonding of these species and the rotation of these CH2 groups. Here in the strained closed structure, you have this sigma bonding here. And then as you open the structure, you have, of course, the allylic pi system. Okay, so once you consider the system a little bit and you look at the literature, what's been done, it has some very, very interesting chemical and physical characteristics. So it has this ring strain, which is sort of a model for ring strain more generally. And it also has, if you notice here in the picture of the radical structure, this alpha hydrogen, which is out of the plane, and it can actually tunnel above and below the plane. This was observed experimentally by David Nesbitt's group. It's one of the high-resolution gas phase infrared spectrum that I note here at the bottom. And there are, in general, very few studies because this radical is not easy to make. There are some matrix infrared studies, there are some ESR studies, and there is a photoelectron spectrum which we're going to discuss in this talk in great detail. And the reason for that is that this photoelectron spectrum is really the only direct thermochemical information that we have about the radical and the cation, and we would really like to sort of get information that allows us to fill in more of this thermochemical network for a few reasons. So the ring strains that I mentioned are of course big players in this network here between the allylic cation and the cyclic cation, and the allylic radical and the cyclopropyl radical. And the other point of interest here is that the CH bond energy of cyclopropane itself is the strongest known alkane bond, again because of this very unusual hybridization that must take place to have this, these very, very strained CCC angles in the cyclic radical. Okay, and of course, as I mentioned here, there's not great agreement between theoretical calculations and the experimental measurements that do exist in relation to the bond association energy. And so we were interested to try to get information about the ring strains of these two cyclopropyl species and to see if there's some information that can be gotten about this question of what are the ring opening mechanisms and why do these cyclic species behave in this way. And essentially the question boils down to the understanding of this photoelectron spectrum that you see here on the left, recorded by Dyke et al. And this is an old F-atom abstraction experiment with a helium photoelectron spectrometer. And at the time, it was believed, based on the best available ab initio calculations, that the cation was a stable structure. And you see it here with the alpha hydrogen here in the plane, because once you've removed the other p electron, there's no reason for that by hybridization for the alpha hydrogen not to be in the plane. And the interpretation of this spectrum is very, very difficult. And so they imagined here courageously some vibrational structure, and that's these ticks here along the top. But it's very unclear how to extract any sort of thermochemical information from this spectrum. And furthermore, when you do modern electronic structure calculations, and this is what's shown here on the right, one-dimensional cuts through the radical and the cation surfaces, the cation is in fact predicted to be a transition state. And so this really makes it a little bit difficult to understand how do we interpret this photoelectron spectrum. And of course, no one has tried to actually simulate this spectrum, and a convincing simulation of this would resolve these questions, and that's going to be our goal here in at least the next portion of the talk. Okay, so just to give you a little bit more of the landscape here of the problem we're attempting to tackle. So you see here the two-dimensional cut of the potential surface of the radical. So this is the deep, broad allylic minimum here. You have one here and one here because remember you can twist one of the CH2 groups all the way around and arrive at a equivalent but distinct allylic structure. And this structure here, this is the cyclopropyl radical here, where we've changed now the CCC bond angle, and also we've rotated these terminal groups from out of the plane into the plane to maintain this pi system here. And you can see this all described in the sort of the coordinate map on the right here. The situation for the cation is different, because what we see here now is that again, we have these allylic, these deep minima here. Let me see if I can get this thing to go all the way over here. So we have, again, 1 and 2 of these, but now we have no minimum here for the cyclic structure. And so what's interesting is that when we superimpose these structures, the projector does not reproduce these well, my apologies. If you can see this here, so what I've taken here is the cation map here on the left and the radical one on the right. In the middle, I've put them on top of each other. And what you can see is that the cyclic radical and the transition state geometry of the cation, these lie very, very close to each other. So when we have this vertical ionization process, the wave function really lands right in this problematic region of the potential energy surface. And so it's going to be a bit challenging to try to simulate this spectrum and to interpret what is the meaning of this spectrum if the cation is not a stable species. Okay. So we set out to do this. We'd done some other similar projects before, simulation of ionization spectra, and we naively thought that we had an approach that would work for this. And so we essentially started with the coordinates that I mentioned to you before that participate most in the ring opening process. And this is, of course, the CCC angle and these rotors that I keep emphasizing. And you rapidly realize that there are several distinct and very important challenges here in simulating the spectrum. So the first is that you have these very, very large changes in the geometry, mostly because of these rotors that go from out of plane to in plane. And then you also have, you find yourself in a very, very high energy geometry above the global minimum on the surface. So the vibrational density of states is very, very high. And all of these things, and of course we're going to a portion of the potential surface that has negative curvature. So all of these things make it challenging to do a simulation of the ionization spectrum. Nevertheless, we forged ahead with what we thought would be a successful approach. And so we begin, of course, with the electronic structure calculations. So these are done with couple cluster in C4. And we use EOM to access the radical, because you see here on the right this sort of three-dimensional map. And these are these avoided crossings which are related to the orbital symmetry problem for the Kahn and disrotatory paths on the radical surface. These are, of course, not very friendly for electronic structure theory, but EOM CC gives us good access to these regions of the potential. And then given our interest in the thermochemistry, we also went ahead and did heat calculations that should give us accurate numbers for the bond association energies and also for the ionization potentials. Okay, so now the question is, how do we approach the simulation of the spectrum? So I'm a frequency domain spectroscopist, and so the way that we like to think about this is that we start from some eigenstate, from a stable species, and then we would excite a transition to some other eigenstate. You calculate all of the Frank-Condon factors, et cetera, and you sum these together to get your spectrum. And so in this situation, though, we're in a different regime where now we're going to a region of the potential surface where there are not they're not bound states, or there's a quasi-continuum of bound states. There's various ways to think about how to approach this. But essentially, it doesn't lend itself to the traditional way of doing things, and it also makes a lot of the calculations very expensive if we have to calculate a full-dimensional potential surface that accesses all of the geometries that this process can reach. So in the time domain, there's a much more natural way to approach this by, of course, taking the Fourier transform of the correlation function of the ground state wave packet that you are transferring to the excited state surface. And so this is the approach that we elected to take in this particular case. And so we started doing these reduced dimension propagator simulations and to see if we could match the experimental spectrum. And before we did that, we went to Soleil. We didn't go because of COVID, but we collaborated with people at Soleil who recorded, now still using F-atom abstraction like the earlier Dike spectrum that I mentioned, but now doing this in a mass-selected coincidence fashion, and you can get from this the threshold photoelectron spectrum, which is free from a lot of the issues in this literature data that I showed you before, and we'll compare those as we go forward. Okay, so now let me show you a little bit how the calculations compare with the experimental data. So let's start with alloradical, which should be a much more straightforward case. This doesn't have any of the challenges that I described before. And you can see here that the agreement between the propagator, reduced dimension propagator simulation and the experiment is quite good. Minus the things like the width of the spectrum, which we can adjust in the simulation, so that's not a big deal. And then one factor that I'm going to come back to here is that we do have to do some empirical shifting because the calculations are not complete. Okay, so now let's see what do we get when we attempt to do this same type of simulation on the cyclopropyl radical. So here at left, you see that in our experimental spectrum, we have some alloradicals it's, I think, very difficult to keep the F atom abstraction from yielding some alloradicals as well. And this here is our, in orange, is our initial simulation of the cyclopropyl ionization spectrum, and you can see that it looks terrible. The position is more or less correct, but the width is completely wrong. And here on the right, I've subtracted the allyl so you can get sort of a closer look, and you can see that still the agreement is not satisfactory in the least. So we scratched our heads for a little bit and realized that we'd made a very silly mistake, and that is that we neglected this other coordinate, which, although it's not integral to the ring opening, still changes quite a bit. This is this position of the alpha hydrogen out of the plane, and so because this changes quite a lot from the radical to the cation, it's very Frank-Condon active, and so we did a one-dimensional calculation that you see here at the bottom and convolved this Frank-Condon progression with the three-dimensional spectrum, and this starts to look more realistic now. This is the comparison between what we would call the four-dimensional simulation here to the allyl subtracted Soleil data. And you can see now that this starts to look closer, but still not what we would call a good match. We can already see, though, that any vibrational structure that one would expect to see, we don't observe that in the threshold photoelectron spectrum. This is different from what was claimed by Dike, and if there's time, I'll discuss that a little bit more at the end. And so now that we've sort of come to the end of the effort that we were willing to invest in these full-scale propagator simulations, we decided to move to a different approach. This is work by my colleague Brian Shangala, who decided to implement something which is, I think the best way to describe it is it's akin to vibrational perturbation theory. And I think that in this audience, most of you are familiar with how to calculate infrared spectra using vibrational perturbation theory. This is a very powerful and convenient approach because it allows you to work with the force field of the molecule as opposed to a full potential surface. And so Brian derived an analytic expression for the autocorrelator function that I discussed before in terms of the force field of the molecule. And this is very, very nice for our purposes here for a number of reasons, not least of which is that force fields are much easier from the electronic structure perspective to benchmark and systematically improve. So if our end goal is thermochemistry a la heat, it's very nice to have a method that we can crank up the knobs on and try to get very good accuracy. So the simulation that I'm about to show you is using really only the quadratic part of the Hamiltonian. There's some minor anharmonic corrections that we've started to implement, but we don't have yet the full cubic and quartic terms implemented in the simulation. And so this is now the Soleil data, where I've zoomed in to give you the more detail on the whole picture here. So you can see here these elliptic sharp peaks here, and then this broad part here is due to the cyclopropyl radical. And when we show the simulation, now this looks much, much better, right? So this is the simulation done at the vertical geometry for the cyclopropyl radical. And if we add to this now the analogous simulation for the alloradical, you see that the red curve traces with the threshold photoelectron spectrum quite nicely, right? So the difference here now is that we're taking the full dimensionality into account, even though it's essentially only in a harmonic way, and we can see that this reproduces this challenging spectrum very, very nicely. Okay, so with this result in hand, we now feel confident to go back to the potential energy surface which is used to generate this simulation and answer some questions about the dynamics and the chemical properties of the radical and the cation that I began the talk with. So these are cuts through the radical and the cation surface, both along the conrotatory and the disrotatory paths, right? These two different ways of twisting the terminal rotors. And you can see some very interesting things by inspecting these plots. So first of all, so as we noted at the beginning, in the radical, you have barriers. This is the cyclic radical geometry here. You have barriers both in the disrotatory path and also in the conrotatory path. But for the cation, you only have them for the conrotatory and not for the disrotatory, right? So this confirms that the cation is indeed a transition state, not a stable species. And the other thing which is very interesting is that if you look at the barrier height along the conrotatory path, you can see that if we look at, for example, the difference in energy from here to here on the blue curve and on the red curve, these are not dissimilar. So in other words, the reason why the radical is a stable species and the cation is not, does not have anything to do with a stabilization of the cyclic structure itself. It has to do rather with these orbital symmetry barriers in the Woodward and Hoffman sense that we talked about at the beginning. In other words, the radical, you can think of it as sort of a kinetic stabilization rather than some sort of difference in bonding or hybridization or something of that sort. So, all right, and also, of course, you can tell from these curves that the ring strains are more or less the same. They differ by about 10%. Okay, so with this, with these computational experimental results in hand, we turn to Branko Ruscic, who works with his active thermochemical tables approach at Argonne National Lab. And he refined this whole thermochemical network, and we come out with more accurate results for the cyclopropane bond association energy, and also for the ring strains of both the cyclopropyl radical and the cation. Okay. And so I want to take the remaining time actually to tell you about an experiment that did not work and some interesting ideas that came out of thinking about this. So in our quest for better thermochemical information about this cyclic system, we naturally wanted to try to close some thermochemical cycles directly. And that's what you see here on the right. So we have now this new value for the, wrong button, for the ionization energy of the cyclic species, and we would like to measure the appearance energy of cyclopropane to provide a direct measurement of the CH bond association energy of the cyclopropane molecule. So this entails essentially going to the synchrotron, putting the cyclopropane in, and looking for the cyclic C3H3 plus species to appear. And the results are shown here. And this is the expected energy where we thought we might see something corresponding to this process in the synchrotron data. And so looking here at the yellow curve, because what happens is that you start by making cyclopropane cation here in the purple, and then this eventually begins to fragment into dissociatively ionize into other species. And so you see here the C3H5, so this is allyl, and then we thought we might see some change in this trace here. And so we didn't see anything, which is perhaps not too surprising given that I just explained to you that the cyclic cation is not actually a stable species. But we did see some changes in other traces right around this energy. And so I'm not going to interpret those changes as a sign of this process that we thought we might see, but it did make us think about what would the effect be of a transition state at this energy? In other words, a bound species, we would have some intuition as to what that would do to this experiment, but what might a transition state do? Might it, for example, funnel the dynamics into increased probability for further fragmentation? And this turns out to be sort of an interesting general concept or discussion here. So humor me for the remaining minutes that we have here. So what is a species? Usually when we think about sort of a general model for a chemical system, we have a double minimum, let's say, a simple model for this. And we have a transition state in the middle of them, and we published a paper some years ago that demonstrated that the density, the vibrational level manifold can be related to the transition state energy. And if you take the inverse of this idea and you look at the density of states, you come across something which is, I think, quite interesting. And so let's imagine for the moment that we are manually calculating by hand the density of states as we start at negative energies. And so we work our way from below this graph here until we hit the first minimum here. And so immediately we have an increase in the density of states, and that's reflected here, this red marker here. And then we continue up, and the density of states does what it's going to do, related to the potential shape. And then we come to this minimum here, and the density of states jumps a second time. And then again, as we continue up in energy, it continues to increase. Again, depends on the shape of the potential. And now we come to the energy of this transition state here. And so since this is a stationary point, the spacings between the vibrational states goes to 0, which means you have a spike in the density of states. And that's what you see here on the right, this spike here. And so what I would like to contend to is that if I showed you this graph on the right here, only up to this green dotted line, you would be hard-pressed to tell me which of these features here, 1, 2, and 3, which of these came from a minimum, and which of them came from the presence of a transition state between minima. And since we know that the density of states through statistical mechanics is really what determines the properties of molecules, this is sort of suggestive that a transition state might not be sort of just the gateway between, between two stable species that we usually consider. Okay, and so my student who's working on this project then had a great idea. He said, wait a minute, why do I need to consider this density of states only versus energy? Why don't we consider it versus geometry as well? And so you can do that by the following procedure. You take the wave functions of this model potential, you plot them coming out of the plane here. So this is, for example, this spike here is the ground state harmonic oscillator function at the bottom of this potential. And then you can bin this plot here, and you can plot basically sort of a phase space density. So both as a function of energy and as a function of position, and this color map is what you come out with. And so you can clearly see that we don't have a buildup of the quantum state density only at the minima, we also have it here at this transition state. So this is, again, not just in terms of energy, but also in terms of geometry. And once you have this type of a plot, you can section this, and you can look at a density of states that is, this plot that you see here on the right is sort of an integrated version over geometry, if you will. So this is a plot now of the one-dimensional cut through the cation, cyclopropyl cation potential that I showed you before. And now what we've done here is we've taken a cut through this, this map here at the geometry of the cyclic species here. And you can see that, as I showed you before, it has this rise and then this fall, which that depends on the outer walls of the potential, is not particularly important for the moment. So if we now take this cut through this phase space map, both at the AL geometry and at the cyclic geometry, and we plot this on top of the experimental data, it looks surprisingly similar. And I think this is not a coincidence. In other words, that in the ionization process, you're sort of accessing this buildup of state density at the transition state. But this means that not just in spectroscopy, but also in dynamics, you could have an effect of this kind. And so this is an idea that we found very interesting as we were considering some of our results. So with that, I will finish here and just summarize the results here, investigating ring opening dynamics through the photoionization spectrum of the cyclopropyl radical and thinking also about the cation. We made some advances in the thermochemistry of this system, and we also have come across this intriguing idea about the behavior of transition states in chemical systems more generally. So I'll be happy to take any questions, and thank you very much for your attention.
Many thanks, Joshua, for this very interesting talk. There is time for questions.
Hi, thank you for the talk. Eric Keller of VTH. So maybe just a comment at first. If you were interested only in the envelope in your optical absorption experiments, I think one could also consider using semi-classical methods, which would allow you to go to full-dimensional treatments, include tunneling, and yeah, basically overcome the other issues you had with the limited dimensionality. Another question I had is, so I'm not an expert on EOS or EOM coupled cluster. Could you maybe elaborate a little bit on how this method can capture avoided crossings?
Yeah, so it's a shame for me to answer this question when John is sitting in the front row, but essentially, so I'll back up for just in case people aren't so familiar with quantum chemistry. So you start with the Slater determinant when you work with the Hartree-Fock method, and then the coupled cluster method describes electron correlation by giving you a linear sum of Slater determinants. The equation of motion method then, and the coupled cluster expansion is organized in terms of excitation operators from the original Slater determinant. The EOM method is just sort of a more flexible option to start from a different single reference and jump into a different set of determinants which can then describe your final wave function. And so it doesn't have to be the same species at all that you want to calculate. You can start from something else entirely with a different charge, with a different multiplicity, what have you. There are many different flavors of EOM because the ansatz at the beginning is so flexible. So in our case, we would start with a stable closed shell reference, and then we come into the radical Fock space, and we're able to get a weighted set, a balanced set of determinants in the final wave function that we obtain without using a multi-reference method. So I'm really not an expert. If you have more questions about this, I refer you to John, but that's my understanding at least.
Thank you very much.
Other questions? So maybe I can ask one. I'm not familiar at all with simulations, but could you go back to these 4D simulations? I think you went a bit fast, so I didn't fully got it.
Yeah, so essentially, usually when one does these sorts of methods, and actually a bit in response to the semi-classical comment, oftentimes the expense is in the electronic structure calculations. Not all of it, but a significant portion of it. So what we try to do is we try to focus on the coordinates, on the parts of the problem that are most essential for getting a simulation which captures the essence of the experiment. And so in this case, we attempted to do that, and we found that because of the extreme changes in geometry, it's really not possible to sort of escape from, to restrict oneself to only a few coordinates. And this is sort of what we were able to do looking at the coordinates that we felt were most important. And after we did this, after we saw that this simulation was not what we wanted to get, then we went to a more creative way to do a full dimensional simulation. But oftentimes one can get away with something like this, and it will work very, very well.
Okay, so I think we can thank Joshua again. So the last speaker of the session is Anita Schneiker, and she will speak about low temperature formation of C-alpha glycine radical as a potential interstellar precursor of natural amino acids. Please, Anita.
Dear audience, the title of my presentation is Non-Energetic Low Temperature Formation of Carbon Alpha Glycine Radical, a potential interstellar precursor of natural amino acids. So the identification of glycine in the interstellar medium, ISM, is uncertain. Attempts have been made to identify glycine in the interstellar medium with radio astronomy, and the identification of glycine based on its rotational spectrum in hot molecular cause was published, but later this discovery was disproved, and the line which was assigned to glycine in the former study were assigned to vibrationally excited ethyl cyanide and vibrationally excited vinyl cyanide and other species in the latter study. So therefore, glycine is currently not counted among the more than 200 interstellar molecules. However, glycine was found on meteorites, for example, a Murchison meteorite, and on comets, for example, Will-2 comet. And in addition, the Rosetta also detected glycine on the comet Churyumov-Gerasimenko. It is very important that glycine was found on comets, because comets come from the outer space, so it is thought that they can reflect the composition of the interstellar space. And in addition, glycine was also found in the atmosphere of Venus, based on the data of LIMA radio telescope. There are several possible mechanisms for the formation of interstellar glycine. I mentioned just a few of them. Lee and Coker generate glycine on interstellar ice analog films composed of water, methylamine, and carbon dioxide under UV irradiation. You can see the mechanism. And the other important work was made by Peeling and co-workers. They performed calculations for several interstellar reactions, both in solid and gas phases. And these reactions involved formic and acetic acid and carboxyl radicals. They would like to know which are the most favorable reactions for formation of glycine in star-forming regions, which are dominated by soft X-ray and UV radiations. To answer this question, they combine theoretical computations by former experimental results. Here you can see the most favorable reactions according to their study in gas and in solid phase. In gas phase, the reactions which involve acetic acid are dominated, and in solid phase, the reactions which involve formic acid are dominated. The problem with these and many other mechanisms is that for formation of glycine, some radiation like cosmic particles, UV or X-ray is needed. But according to former laboratory experiments, during this irradiation, glycine can decompose. So if glycine form according to this mechanism, they cannot accumulate in the interstellar medium. Therefore, it is very important, the experiments which was performed by Apollo and the co-workers, they shown that in the presence of hydrogen atoms, which present in the core of dark molecular clouds, glycine can form from carbon monoxide, methylamine, and oxygen. Other important experiment was made by Yoshi and co-workers. They can detect the formation of carboxymethyl radical in solid parahydrogen from acetic acid in the presence of hydrogen atoms. According to previous theoretical models, glycine can form in the reaction of NH2 and carboxymethyl radicals. So it is other experimental evidence the formation of glycine according to a non-energetic mechanism. Other possible mechanisms will be present on Friday by Yoshi. So the motivations of our study were to investigate the reaction of glycine with hydrogen atoms, identify the reaction path and the product, understand if these reactions can destroy glycine in the space, or rather they can be important intermediates in the formation of amino acids. It is important to mention that Tsako and co-workers investigated the conformers of the hydrogenated glycine radicals. There are three possibilities for the hydrogen atom abstraction. Hydrogen atom can be abstracted from the carbon alpha atom. In this case, there are 4 conformers of the form radicals. And the hydrogen atom can be abstracted from the nitrogen atom, in which case the form radical has 7 conformers. And the third possibility is when hydrogen atom abstracted from the carboxyl group, in which case the form radical has 4 conformers. And according to this study, the lowest energy, the hydrogenated glycine radical is this carbon alpha glycine radical. Here you can see the potential energy surface of the reaction of glycine 1p conformer with hydrogen atoms. Here the hydrogen atom abstraction, and here the hydrogen atom addition. And we can see that the reaction which results in the formation of the lowest carbon alpha glycine radical has the lowest barrier. So we can accept that the lowest energy carbon alpha glycine radical can be a product of the reaction of glycine with hydrogen atoms. But the other hydrogen atom abstraction reaction also has small barriers, and so the experiments are very important to identify what are the most effective reactions. And according to former studies, these small reaction barriers can be permeable for hydrogen atoms by hydrogen atom tunneling at low temperature. The potential energy surface of the 2N conformer of glycine is qualitatively similar, and the potential energy surface of 3N conformer of glycine resembles even more that of 1p conformer. One difference is the conformation of the carbon alpha glycine radical, but the barrier between the conformers is very small, or the hydrogen atom tunneling can be very fast, so we can accept that the reaction heat can be enough to convert the high energy conformer to the lowest energy conformer. And here you can see the expanded potential energy surface, and here there are other reactions which can take place. For example, the formation of aminoacetic acid. The experiments were performed in an ultra-high vacuum chamber, and the glycine was evaporated by a stainless steel oven. The matrix was deposited to a gold-plated silver wafer mounted on a cold finger of a cryostat, which allowed to cool down the substrate to 3.1 Kelvin. The reactions were followed by IR spectroscopy, and the spectra were analyzed by the help of quantum chemical computations. Here you can see the mirror spectrum of glycine in parahydrogen after deposition. In correspondence with former argon matrix experiments, there are 3 conformers in the matrix, 1p and 2n and 3n conformers. On the spectra, I labeled only just the most intense bands of the conformers. And to investigate the reaction of glycine with hydrogen atoms were generated by the method which was discussed on Monday by Professor Lee and Shandor Gobi. And here you can see the difference spectrum, which was obtained by subtracting the spectrum taken before hydrogen atom generation from the spectrum taken after hydrogen atom generation and waiting few hours in the dark. We can see that the amount of the glycine conformers decreased, so glycine can react with hydrogen atoms. And we compare the experimental spectra with the computed spectra of spaces which can form from glycine by hydrogen atom addition or by hydrogen atom abstraction reaction. And we can conclude the main product of the reaction of glycine with hydrogen atom is the lowest energy carbon alpha glycine radical. In addition, in a second hydrogen atom abstraction reaction, one conformer of aminoacetic acid also formed, and the assignment of this conformer, which you can see later, was supported by the help of the secondary UV photolysis. We investigated what happened if we changed the conformer ratio of glycine. To this, we prepare a 1p, a 3n, and a 2n enriched matrix. And to change the conformer ratio of glycine, selective near-IR laser irradiation is needed. Here you can see the carbonyl stretching region of the spectra of glycine. The spectra from A to D are the spectra before hydrogen atom generation in the 4 different cases, and the spectra from E to H are different spectra for the 4 different cases. We can see that in all cases, the lowest energy carbon alpha glycyl radical formed. So we can conclude that regardless of the conformation of glycine, the lowest energy carbon alpha glycyl radical can form with high selectivity. After hydrogen atom generation and waiting few hours in the dark, we examined the effect of 280 nanometer photolysis on the carbon alpha glycyl radical. Here you can see the different spectrum, which was obtained by subtracting the spectrum taken before 280 nanometer photolysis from the spectrum taken after 280 nanometer photolysis. And you can see that the amount of the carbon alpha glycyl radical decreased, and the amount of the remained glycine conformer is unchanged. The products of the decomposition of carbon alpha glycyl radical are different conformers of aminoacetic acid. Among the possible 8 conformers, 4 was clearly identifiable in the matrix. And these conformers formed at different rates, so the bands which belong to these conformers can be grouped, which can help the assignment. It is important that these aminoacetic acid conformers formed by the nitrogen-hydrogen bond rupture, which process generate hydrogen atoms. To supporting this statement, we let the matrix in the dark after the 218 nanometer photolysis. And here you can see the different spectrum, which was obtained by subtracting the spectrum taken after 218 nanometer photolysis from the spectrum taken after 218 nanometer photolysis and waiting few hours in the dark. Here we can see that the amount of the glycine conformers and the amount of the aminoacetic acid conformers decreased, and we can see the formation of the lowest energy carbon alpha glycine radical. Although the bands of each aminoacetic acid conformance decreased, but we can see the formation only this carbon alpha glycine radical. As a summary, we can say that glycine can react with hydrogen atoms in a hydrogen atom abstraction reaction, results in the formation of the lowest energy carbon alpha glycine radical with high selectivity, and this product is regardless from the conformation of glycine. And in a second hydrogen atom abstraction reaction, aminoacetic acid also can form. And the aminoacetic acid also can react with hydrogen atoms in a hydrogen atom addition reaction, which results in the formation of a carbon alpha glycine radical. So we can conclude that a quasi-equilibrium has to exist between glycine, carbon alpha glycine radical, and aminoacetic acid in the presence of hydrogen atoms. The question may arise why these experimental results are important. So according to our experiments, we can say that carbon alpha glycine radical can be formed in the conditions relevant to interstellar dark molecular clouds. And it is also important that the reactive radical center of the carbon alpha glycine radical is on the carbon alpha atom. So it can be a precursor of a formation of other amino acids. So we can conclude that natural amino acids can be formed from glycine via carbon alpha glycine radical in the solid phase of the interstellar medium. This statement was investigated theoretically by Shivani and co-workers. According to their calculations, serine can form from CH2, OH, and carbon alpha glycine radical in conditions relevant to interstellar medium. Our future goal is investigate this statement experimentally. We have already done experiments in parahydrogen matrix and in ice. Glycine was deposited with methanol, chlorine, and parahydrogen, and the hydrogen atom were generated by laser irradiation. And we can see the formation of carbon alpha glycine and hydroxymethyl radicals. And after hydrogen atom generation and waiting few hours in the dark, the matrix was annealed to soften it. And we also performed experiments with glycine methanolysis, in which case the hydrogen atom were generated by hydrogen atom beam source. Although we can't see the formation of serine in these experiments, but we hope if we can optimize the experimental conditions, we can generate serine and report it in the near future. And thank you for your attention.
Thank you, Anita, for this nice talk. Are there any questions? Yeah.
Vladimir Feldman from Moscow. Thank you for a very interesting talk. I did not catch on your slide what do you mean saying CH2 radical. CH2 is not radical. It's a carbon with ground singlet state. What is CH2 radical? It doesn't exist. Just misprint. Because CH2 is not an open shell species. It's a carbon. So you meant probably CH2OH radical, yes, produced from methanol or from something else. Yes? Yes. Okay, thanks.
Maybe it's a question of terminology. So, did you get the question? So maybe you can say it again, but put the mic a bit closer.
No, I think that's a misprint there. So that's
okay. Are there any other questions? So maybe I have one. So you showed many reaction pathways, many complex reaction pathways, in fact, and I was wondering whether experimentally you could try to favor one of these by tuning something like the wavelength of the laser or whatever. Because you need to irradiate your parahydrogen matrix containing chlorine. So can you try to favor some of these pathways by tuning the laser?
So I investigated the reaction of glycine with hydrogen atoms. So we generate hydrogen atoms with laser irradiation.
I'll rephrase it. What happens if you change the wavelength of the laser? Could you try to have one pathway, another pathway?
Interrupt you, it's a reaction with hydrogen atom. So the first laser radiation was used to generate hydrogen atoms. You don't touch the glycine, okay? The glycine do not photolyze at 365. So these reactions, not photochemical reactions, these are reactions with hydrogen atom. There is a secondary photolysis, when you photolyze the products, okay? And we did change the photolysis wavelength, and we saw a little bit shift between the ratios of amino acids.
All right, I think we can thank all the speakers again. So maybe there is a